All right, here we're going to look at problem number 1 on the 14.3 worksheet that says to compute the double integral of the function 1 over the quantity x squared plus y squared to the 3/2 power, where R is the region shown below. The curved portions of the boundary are parts of circles centered at the origin. Okay, so this region R is one of these polar rectangles that we defined in the last video. And if I go ahead and set this up using rectangular coordinates, let's say I want to use horizontal strips, okay, I would get something like this. I'm actually going to have to break this up into two integrals, okay, because you can see in the figure that I'm going to have to go from the inner circle to the outer circle. And then at this point where the inner circle intersects this red line, I'm then going to have to transition because up here I'm going from line to this outer circle. Okay, so I have these two integrals whose bounds of integration are pretty messy, and the integrand here is by no means simple. I'd have to use trig substitution. So yeah, I really don't want to compute something like this, right? What if I use vertical strips instead? Well, that would actually be even worse, because now I'm going to have to split things up into three pieces. Okay, I'm going to have this first integral that's corresponding to where we go from inner circle to line, and then I'm going to have to go from the x-axis up to the line for the second integral, and then this last integral is going from x-axis to this outer circle, right? So this is even worse, okay? So what about polar coordinates? Let's look at the integral doing that. Well, in the last video, okay, one key thing that we saw was that the differential element, dA, this was r dr d theta, right? We had that factor of r there. And the other thing to notice is that in this denominator, I see the expression x squared plus y squared. And in polar coordinates, that's simply r squared. All right, so then to compute this as an iterated integral in polar, well, our dA would be r dr d theta, and then down in the denominator, we're going to have the quantity x squared plus y squared, which is just r squared, and then that's being raised to the 3/2 power. Okay, so this is significantly simpler, okay, than what we have up here. What about the bounds of integration? Well, those are pretty simple too, right? Because to fill out this region R, theta is just going from 0 to pi over 4, and R goes from 1 to 2, okay? So if I'm going to compute this as a dr d theta integral, R then would go from 1 to 2, and theta is going from 0 to pi over 4. Okay. Now, before we go ahead and finish this calculation, I want to highlight one thing here, that when we talk about integrating with rectangular coordinates, we think about filling out the region either with vertical strips or horizontal strips. So when you're integrating in polar coordinates, you want to think about filling out your region with a bunch of sweeping rays. Okay, so what am I saying there? Think about first fixing a theta. So if I fix a theta, I'm really describing a line through the origin. So here's our fixed theta. And now, right, for my region, well, I see that that ray, it enters in right here, where r is equal to 1. And then it's exiting out here, where r is equal to 2. Right, so we're looking at this ray right here. And now, as we let theta range from 0 to pi over 4, we're going to fill out this region R, right, with these blue sweeping rays. Okay, cool. So with all that now in place, let's go ahead and compute this thing. So this expression down in the denominator, r squared to the 3/2 power, is just r cubed. And then r over r cubed would leave me with a 1 over r squared. So I'm looking at the integral from 0 to pi over 4, and then integral from 1 to 2, and we're saying I got dr d theta over r squared. Okay, so now I'm doing the r integral first and integrating 1 over r squared would give us minus 1 over r, and then evaluate from 1 to 2, and this right here is going to give us minus a half minus a minus 1, which is equal to just a half. Okay, so I'm really just integrating now a half. So I'm going to get theta over 2 from 0 to pi over 4. So it looks like the value of the integral is pi over 8. All right, not too bad, especially in light of what we would have had to have done if we use rectangular coordinates, right? This is significantly easier. Okay, now the last thing I'll say here before we finish is that if you go back to this step in the calculation, there is a way we can simplify some of this work that followed. So the thing to note is that the integrand 1 over r squared does not depend on theta. Okay, so this inner integral right here of 1 over r squared here, this thing is totally independent of theta. This is just going to give us a constant. And so I can in fact pull this out in front of the theta integral. So I'm looking at the integral from 1 to 2 of 1 over r squared with respect to r. And what am I left with? Well, just the integral from 0 to pi over 4 d theta. Okay, and so we've seen this kind of thing before back in sections 14.1 and 14.2. This theta integral is just the length of that interval. It's just pi over 4. And the integral here of 1 over r squared, that's going to give us a half. So this part is a half. And so there is your pi over 8. Okay, so this isn't a completely necessary step, but it really can help you speed some of this up. And we'll see it come up quite a bit as in the next couple examples. So keep this kind of thing in mind. So if your integrand is independent, say, of theta, this outer theta integral is really just acting as a multiplier, right? It's going to multiply this inner integral by whatever the length of this interval is. Okay, great. Well, stop there. Thanks.